Hi everybody, I am Dr. Savitri, Professor, St. Joseph's Institute of Technology, Chennai. In this video, we will see the different types of mass diffusion mass transfer and we will solve problems on each type. Okay, so the first type is steady state diffusion of component A through the membrane. Second one, steady state equimolar counter diffusion of component A and B. And third one is steady state evaporation of component A into stagnant air. Okay, so first we will see the steady state diffusion of component A through the membrane. Actually, this is similar to the steady state conduction through wall. In heat transfer, the conduction equation is Q is equal to delta T by RT conduction, that is a thermal conduction resistance. Similarly, here in mass transfer, it is mass transfer is equal to concentration difference divided by RM diffusion, mass transfer diffusion resistance. So the equations are similar for heat transfer and mass transfer. Now we'll compare that. So if you consider a plain wall, the conduction resistance, thermal conduction resistance is L by Ka. So the mass diffusion resistance is L by DAB into A. So if you compare these two, here in mass transfer, the K is replaced with the diffusion coefficient DAB. Similarly for cylinder, here it is ln of R2 by R1 by 2 pi L into DAB instead of K, DAB. For sphere also instead of K, we will use DAB. Okay, so now we will try to solve one problem in mass transfer. Okay, so the problem is hydrogen gas, okay, is maintained at 3 bars and 1 bar on opposite sides of a plastic membrane which is 0.3 mm thick. The temperature is 25 degrees Celsius and the binary diffusion coefficient of hydrogen in plastic is 8.7 into 10 power minus 8 meter square per second. The solubility of hydrogen in membrane is 1.5 into 10 power minus 3 kilogram mole per meter cube bar. What is the mass diffusive flux of hydrogen through the membrane? Okay, this is the problem. So first we will see what are the data given. Okay, so the given data are the pressure on either sides of the membrane is given, membrane thickness is given, and DAB is given, diffusion coefficient is given, solubility is given. This will be useful to find the concentration. Okay, so these are the data given. So what we have to find is what is the mass diffusion flux or mass transfer rate that we have to find. Okay, actually we have the equation for molar transfer. We know the equation for molar transfer. So mass transfer is equal to molecular weight into molar transfer or molar flux. Okay, so the molar flux, the equation is delta Ca divided by resistance. Here plain wall resistance we know. Okay, so now first we have to find what is delta Ca, that is this side Ca1 and Ca2, concentration of hydrogen and concentration of hydrogen on other side. Okay, so this side the concentration, the data is given is the partial pressure and we know the solubility of hydrogen in this membrane. So we know the equation concentration is equal to solubility into partial pressure. So we'll get 4.5 into 10 power minus 3 kilomole per meter cube. Next, same way we can find what is Ca2. So we know the partial pressure at this end 1 bar. So it is 1.5 into 10 power minus 3 kilomole per meter cube. So next we have to find what is the resistance. So the resistance, we know that it is L by DAB into A. So L is the thickness 0.3 mm. So into 10 power minus 3 meter. and DAB is the diffusion coefficient, which is given as 8.7 into 10 power minus 8 meter square per second, and the area, it is not given, so per unit area we will take, so it is equal to 1. So we got the resistance. Now Na equal to delta Ca, that is Ca1 minus Ca2 divided by R. So it is 8.7 into 10 power minus 7. So now we know this Na value, and if we multiply by molecular weight of hydrogen, then we will get what is the mass flow. So molecular weight of hydrogen is 2. So 2 into this Na, it will give 1.74 into 10 power minus 6 kilogram per second per meter square for unit area. So this is the answer. Okay, so the second case is steady state equimolar counter diffusion of component A and B. Okay, now we'll take this case. We'll have two containers, and in this container we have gas A. The concentration of A is high, or initially we'll take this left side container, it contains a gas A, and the right side container, it has gas B. Now these two containers are connected by tube. If we open this tube, what will happen is here gas A concentration is high, and this side the gas A concentration is almost 0. So this gas A, it will try to move towards the right. At the same time, the gas B, here this side concentration is high, on the other side it is almost 0 initially. So this gas B will also try to diffuse or come to the other side. So here what will happen is gas A, it moves in the right side, and gas B, it moves in the towards the left side. So at any particular point, if you see that in any area, you see that the number of moles of gas A crossing will be equal to number of moles of B crossing. Okay, that means here the number of moles will be equal, that is Na will be equal to Nb, but it will be in opposite direction. The diffusion rate will be same, but it will be in the opposite direction. That's why Na is equal to minus Nb, or Na plus Nb is equal to 0. Okay. So now the molar diffusion rate will be same, but the mass diffusion rate is not equal. Na is not equal to Nb, because Na, it depends on that molecular weight. So molecular weight of different gases are different. So you should be very clear that the mass transfer rate will not be same, but the molar transfer rate will be equal. Okay, so the formula, if we see from the data books, it's available for equimolar counter diffusion of gases. The molar rate is minus DAB into 1 by RT into dP by dy. So here dy is the distance. Here it is shown as x or L. Okay, so here we are using y2 minus y1, that is the length of this tube. Okay, so in molar terms, here the R is universal gas constant. In mass terms, it is a specific gas constant Ra. So Ra is equal to R universal gas constant divided by molecular weight of A. Okay. So now we'll solve one problem. Okay, so now the problem is CO2, carbon dioxide and air experience diffusion through a circular tube of 50 mm diameter and 1 meter long. The system is at 1 atm atmospheric pressure, 25 degrees Celsius. Partial pressure of carbon dioxide at one end of the tube is 190 mm of Hg, and the other end of the tube is 95 mm of Hg. Determine the mass rate of flow of carbon dioxide and air. So here in this problem, carbon dioxide and air, it diffuses through a circular tube. So both the gases will diffuse. So it is a equimolar counter diffusion problem. Okay. So now we will solve that problem. The given data So what are the data given is the total pressure is 1 atm, which is equal to 1.01325 bar. The diameter of the tube is 50 mm, so 0.05 meter. So the length of the tube is 1 meter. The temperature is 25 degrees Celsius, so plus 273, it is 298 Kelvin. The pressure of carbon dioxide one end is 190 mm of Hg. The other end, the pressure of carbon dioxide is 95 mm of Hg. Then what to find is the mass flow rate of carbon dioxide and air. So here it is a equimolar counter diffusion. So first we have to convert this unit 190 mm of Hg of pressure into bars or Pascal. Okay. So atmospheric pressure is 760 mm of Hg, that is equal to 1.01325 bar. Therefore, for 190 mm of Hg, it is 0.25 bar, 3 bar, and 95 mm of Hg, 0.127 bar. So for equimolar counter diffusion, so the molar concentration of carbon dioxide is equal to molar concentration of air, but the mass concentration are not equal. So first we will find DAB, diffusion coefficient, from data book we will find. So Na by A is 6.023 into 10 power minus 8 kilomole per meter square second. So Na is into multiply by area, pi by 4 d square. So we will get 1.183 into 10 power minus 10 kilomole per second. So from this molar flux we will find out mass flux or mass flow rate. So mass flow rate m of carbon dioxide is equal to molar flow rate into molecular weight of carbon dioxide. For carbon dioxide, the molecular weight is 44. Same way, N of air is equal to N of carbon dioxide. So it is equal to 1.183 into 10 power minus 10. Therefore, mass flow rate of air is equal to N of air into molecular weight of air, which is equal to 1.183 into 10 power 10. Molecular weight of air is 29, so it is equal to 3.43 into 10 power minus 9 kg per second. So this is our answer. Okay, so the third case is steady state evaporation of component A into stagnant air. Okay. So now we will consider a container which is having a height of y2 minus y1, and the bottom the liquid is there and it is open to atmosphere. So what will happen is the liquid, it will try to evaporate from this surface, and during this evaporation only the liquid in its vapor state, it will diffuse through this atmospheric air. The air will not diffuse into the liquid. So that is why it's a steady state evaporation of component A into stagnant air. Okay. So NB, B is air, so NB is equal to 0. Okay. So the equation, if you see, the evaporation rate in mass terms is DAV into total pressure divided by RA, specific gas constant, into temperature into the distance y2 minus y1 into natural logarithm of PB2 divided by PB1. What is PB2 is, B is air. So partial pressure of air at this point 1 is PB1. Partial pressure of air at this end PB is PB2. So most of the cases are here at the end the PB2 will be equal to the atmospheric pressure. Only at this end PB1 we have to find, we should know what is the partial pressure of air. Okay. So now we will solve the problem. Okay, so the next problem is determine the rate of evaporation of water from bottom of a test tube of 10 mm diameter, 150 mm long into dry stagnant air at 5 degrees Celsius. So the rate of evaporation of water from bottom of a test tube. Okay, now we'll solve the problem.
The given data are the diameter of tube is 0.01 meter, length of the tube, that is y2 minus y1, is 150 mm equal to 0.15 meter. The temperature is 25 degrees Celsius, so plus 273 equal to 298 Kelvin. So here what is find is what is the mass flow rate of water vapor or evaporation rate. Okay, now we will see how to solve. So what is given is a test tube is given. So in the bottom you have the water and the height of the tube or length of the tube y2 minus y1 is given as 150 millimeter. So here air is the atmospheric air is there. This is 0.1, this is 0.2. So the total here the air is atmospheric at atmospheric pressure. So from this what we can write is here component A is water vapor, component B is dry air. Since it is dry air, here the partial pressure of the air is, so normally the total pressure equal to, if at point 1 if you see total pressure, it is PA1 plus PB1, that is same as at point 2 PA2 plus PB2. Total pressure is constant at any point. Okay, so the total pressure is constant at any point. Since it is a dry air, at this point the pressure of water vapor is 0. So the total pressure is pressure of air. So PB2, which is atmospheric pressure, 1.01325 into 10 power 5 Pascal. Now we will see what is the equation for evaporation. From the data book you can find this equation. We should know the values of all the properties. So from data book we can get DAB is equal to 2.58. So diffusion coefficient of water into air, total pressure is, so RA is gas constant of water vapor equal to universal gas constant by molecular weight. It is 8314 by molecular weight of water vapor is 18. So it is 462 joules per kilogram Kelvin. Okay, so now we got our temperature is 298, y2 minus it's given. We want to find what is PB1 and PB2. So PB2 is atmospheric pressure. So what is PB1 is? PB1 is equal to total pressure minus PA1. So from this, okay, so now we can find what is PA1. To find PA1 is equal to saturation. PA1 is saturation pressure of water vapor at point 1. So from steam tables, so PA1 is saturation pressure of water vapor at point 1. So this from the steam tables we can find, we know the saturation temperature 25 degrees Celsius. So at 25 degrees Celsius from pressure table, saturation pressure table, PA1 is equal to 0.03166 bar. Okay, therefore PB1 is equal to 1.01325 minus 0.03166 equal to 0.98159. So PB1 is 0.98159 into 10 power 5 Pascal. So now you substitute all the values here and find what is mass flow rate. Equal to area is pi by 4, d squared is 0.01 square. So the rate of evaporation of water vapor is 3.16 into 10 power minus 10 kg per second.
Thank you. Thanks for watching.